So what we're going to talk about is pre-combustion capture on various systems. And pre-combustion basically means turning the fuel into hydrogen and then burning the hydrogen instead of a fuel. If you burn hydrogen, you can't release carbon dioxide. And also, I'll say a bit about oxyfuel. Oxyfuel means burning the fuel in oxygen. If you do that, you just generate essentially pure CO2 plus water vapor, and that's a relatively easy separation. And separating oxygen from air is also relatively easy and well proven. So the details, we'll talk about some of the principles of hydrogen production, some of the application examples in the UK, talk a bit about gasification for hydrogen production, some experience on coal and aspirations for biomass, and then principles of oxyfuel combustion and a bit about the alum cycle. There's a couple of resources around. One is a seminar that we ran about a year ago, looking at hydrogen production from methane with carbon capture and storage in the UK. This was actually to help a BAT review process that the Environment Agency and other regulators were then going to commission on hydrogen production from natural gas. And the question was really, okay, but what technologies need to be reviewed? And I think it turned out there are actually rather more technologies that were being considered in the UK than people were generally aware of. So we had this seminar. You can follow up the links. I'll be talking a bit about some of the links as well, and see what people said they were thinking about a year ago. And indeed, I'm sure there's a number of other things that have come up since then too. So Hannah showed the diagram very like this. I've actually added a few bits to it. So we're looking at pre-combustion. So we're taking fuels, mixing them with some oxygen, not enough to burn them, and steam, and making hydrogen. And then using the hydrogen for power and heat. Don't think you'd use hydrogen made from fuels to convert back to fuels with CO2. We've got a route over here that does that, but that's likely to be using hydrogen if you're taking hydrogen from electrolysis and mixing it with CO2 taken from the air. So this is hydrogen essentially to make power and heat. You're burning it instead of a fuel containing carbon. One way that's coming up and quite a lot at the moment is actually not burning hydrogen only, but mixing a percentage of it with natural gas. And this is just a straightforward calculation where if you look at the percentage of hydrogen by volume in a blend with natural gas, then you replace a certain fraction of the calorific value of the natural gas and hence a certain fraction of the CO2. And it's not a linear function of the percentage of hydrogen, because hydrogen per unit volume has a lot less energy than natural gas. So common blend that's being talked about is 20% hydrogen in natural gas. And as you can see, that gives you a CO2 saving of about 20%. And if you're burning in a gas turbine, current gas turbines with natural gas, maybe I think up to about 40%, again, relatively low CO2 saving, less than half of that. You have to get up essentially to burning pure hydrogen to get the real savings. And in gas turbines, that's something that's promised to come along around 2030, but it's not actually feasible with current technology. You have to dilute it either with natural gas or with steam or nitrogen. Anyway, that's just a comment. It's an easy calculation, but it sometimes gets overlooked that people assume that the percentage by volume is the CO2 saving, and unfortunately it's not. So a bit of chemistry, try not to get too involved. Fuels are a combination mainly of carbon, hydrogen and oxygen. Energy coming from the carbon and hydrogen, but particularly something like biomass can have quite a lot of oxygen in it. To make hydrogen, you react the fuel with steam, H2O, and possibly some molecular oxygen, O2. And the objective is to convert as much of that carbon in the fuel to carbon dioxide as you can. What you don't convert to CO2 will end up mainly as carbon monoxide. And then hydrogen comes from the hydrogen in the fuel, and also from H2O that's given its O to CO2 and left H2. It's a two-stage process. The first stage is to make a synthesis gas mixture, which is a mixture of carbon monoxide, carbon dioxide, hydrogen, and water by reacting the fuel, maybe CH4, either with just steam, where you have to supply heat externally because this is a reaction that needs heat, or if you don't want to supply the heat externally, and we'll look at how you do that in a moment, then you can partially burn some of the fuel with oxygen and put that in with the steam and generate the heat internally. And those processes known as autothermal reforming, partial oxidation, gasification, all essentially the same process. And then you take this mixture of carbon monoxide, dioxide, hydrogen, and water, and you put it through a shift reactor where the aim is to shift most of the carbon monoxide to CO2. And you've got this sort of equilibrium. It can go either way. You've got these products that you don't want, the carbon monoxide and the hydrogen, and these products that you do want, carbon dioxide and hydrogen. And you want to try and push the reaction in this direction. One way you can push it is to put more water in the mixture, more steam, and that will give you lower temperatures. The other way you can do it actually is to take the products out as they're formed, and that sort of pulls the reaction over in that direction. And Bayes have put 7.5 million into a pilot unit at Cranfield University to look at actually ways of removing the products during the shift. Okay, this is a slide showing a range of different options, and I'm not even going to begin to try and describe them. The takeaway is there's a lot of options for making hydrogen, even more than shown here. But hydrogen is a relatively new development. It's hydrogen with CCS. So I'm not going to try and say which is the best way, which is the lowest cost way, or anything, because the cost and performance in the UK are going to be determined by the ongoing FEED studies and subsequent full-scale projects. It really is an area that's under development, as we'll see. So instead of look at the basic way of making the syngas, synthesis gas. So this is a diagram produced by IEA greenhouse gases. This is a steam methane reformer. You've got little flames, essentially multiple flames, producing heat, which goes into these tubes. You get a mixture of steam and methane, going through the tubes, and that ends up as a synthesis gas with about 70% hydrogen, 850 centigrade. If you're using an autothermal reformer, you have a flame where you're partially burning methane with oxygen and some steam. The gases go through the catalyst bed, and then you make a hotter syngas with about 65% hydrogen, probably about 10–20% methane, carbon monoxide rather. And then finally, if you want to go for really high temperatures, you don't need the catalyst. You get what's called a partial oxidation reactor. You get a flame, and you get combustion products with about 50% hydrogen and some CO2. And all of these processes are perfectly reasonable processes to use. Now, the second stage, the shift reaction, takes place in two stages, and the proportions of the CO, CO2, H2, and H2O are governed by a chemical equilibrium reaction. So you can only get certain proportions at a given temperature. So there's a limit on what you can do. And if you make more hydrogen and CO2, you release heat. So you're starting over here somewhere with the synthesis gas. You're doing a high temperature shift. And in this case, you get down to about 3% carbon monoxide You can't get any more because you've reached the equilibrium line. So you have to cool, and then you're ready to react again in a low temperature shift bed. And then you can get down to about 0.5% carbon monoxide. And this sort of process is common to all of the routes for forming hydrogen. This technology is very well understood. It's quite old technology, but as I say, the bit that isn't understood is if you want to have some sort of shift that's aided by removing the products as they form. That's new technology. If you do that, then you'll probably have to add less steam and water. That's the whole idea. But if you can do that, you'll save on the energy and cost. Okay, I mentioned the seminar that we held. This is it. It's showing all of the different speakers. We had a number of technology providers, and we also had a number of projects, or the ones we knew about at the time. And the link is in the slides. You can go and have a look and see what they said, although there'll be a lot more information now in the public domain. Some factors that will be important in the technology selection for producing hydrogen from natural gas with CCS, obviously the level of CO2 capture that can be achieved, the operating costs where the conversion efficiency will be the main differentiating factor. Sort of numbers I think we are expecting are in the region of 75 to 80% of the heating value of the fuel ending up in the hydrogen. Obviously capital costs be very important, and also the cost of capital. You can't forget that. You know, you may have something that's theoretically cheaper, but if it's riskier and it costs more to finance, it doesn't give you an advantage. Also a question about the scale, with steam methane reformers generally being preferable at smaller scales, and ATR or POX at larger scales. Flexibility will be important, especially if you don't have storage. People are looking at salt caverns for storage of hydrogen. Some projects, I think, are looking at retrofits because we've got existing steam methane reformers in refineries, and those can be retrofitted with post-combustion capture, as we'll see. And there are already a range of studies comparing these options, and I've given a few links below, but to be honest, I wouldn't take the results too seriously, because you need to consider local conditions and you need to look at real engineering. And so, you know, the real answers will come not from theoretical studies or some generalized studies, but what we actually see on plants in the UK. Having said that, let's have a look at the characteristics of some of the examples. So one example is, as I said, steam methane reformer plus post-combustion capture. This is something that was produced in a study for bays by Wood. So you've got the reforming stage, you've got the shift stage, and then you're taking out the hydrogen product and you're left with carbon dioxide, some carbon monoxide, and converted methane. You take that back, you burn it on the outside of the tubes in the furnace along with more fuel, and then you can capture essentially all of the carbon using a post-combustion capture plant. And essentially the performance capture level is determined by the performance of that post-combustion capture plant, which it might be as high as 99%. So potentially quite high levels of capture from this route. There is actually a steam methane reformer with capture, but it's not capturing the CO2 from the furnace, so it's a low level of capture. But Air Products have run a unit in the USA very successfully, and they've captured by mid-2020 6 million tons. I think it's probably close to 7 now. They sent it into the pipeline system for enhanced oil recovery. They used a technology which they said was superior to amines. This is for not the flue gas capture, but the capture at high pressure from the shifted syngas. So that's an option, but I don't think that option would work in the UK because you're limited to, I think, 65, 70% capture. Something that might work in the UK, if you want to produce hydrogen and electricity on the same site, and you certainly do have sites that are producing both, is instead of using air, in the steam methane reformer furnace, you can use gas turbine flue gas. And that's actually done at Port Arthur on that example I just showed you. If you do that, then you can do post-combustion carbon capture. It doesn't say post-combustion, but it is, from both the gas turbine flue gas and from the steam methane reformer flue gas, and you can save some on the capital cost and operating costs. And this is something that the UKCCSRC has developed as part of its core research, and we certainly have talked about it a bit with a number of the UK projects. Another option, which you've seen described, is the Shell blue hydrogen process. This is a slide from the seminar showing what's going on, and this is high temperature reaction with oxygen from an air separation unit, and then the shift, proprietary CO2 capture technology to take the CO2 out, and you're left with nice pure H2 to deal with. Another concept that was described by Matthew in the seminar is their leading concept hydrogen. They have again reformer shift, CO2 removal, hydrogen separation, and then they fire the empties, fire the residual. The benefits stated for this are a lower methane content in the reform gas, a low CO slip, in other words, high conversion of CO to CO2, and the CO2 is captured at pressure, so it's ready to compress, which is better than post-combustion capture in a steam methane reformer. So these are claimed benefits. Bayes has funded a feed study on this process for HyNet, and it's also been looked at for Acorn, so we'll get some real answers. You could look at more details in the seminar, and there'll be more details in various places on the internet. Something that has been looked at, I was sort of mentioned this project in the chat at the start, is electric power production from hydrogen using pre-combustion capture. This has actually been looked at a lot more really than hydrogen production with CCS, I would say, just an integrated system producing power. And this is an example from about 2005, 2006, where you're using an autothermal reformer, in this case with air as the feed, not oxygen. You're producing a mixture of hydrogen, carbon monoxide, and nitrogen, shifting it same way, it's not affected by the nitrogen apart from diluent. You're taking out the CO2, and then you're burning hydrogen and nitrogen in the gas turbine. And because you've got some nitrogen in there, you can burn pure hydrogen as well. So you can get good conversion. And then your only product is CO2. And this was proposed by BP for the first project, Decarbonised Fuel 1 at Peterhead. In 2005, it was actually announced, I think, at the Glen Eagles conference, sort of the equivalent of COP26 at the time. Used proven technology for all of the components, which was good, but the project was announced as June 2005, but it was cancelled mid-2007. And it's worth thinking about the reasons for cancellation. So it was pre-combustion on gas to power, and that actually looks uncompetitive, except when hydrogen can be stored for peaking plants. And if you can store the hydrogen and you're running the power plant for short periods of time, then you can run the run the hydrogen production plant all of the time and make it effectively a much smaller size. So if you say the peaking plant's running 10% of the time, you only need 1/10 of the size on the hydrogen plant. So you can save money there. But that wasn't done. This was a baseload plant. As you can see, it's a separate plant. It didn't integrate at all with the gas turbines on the existing Peterhead power plant, so it cost more than it should have done. And then also by 2007, there were serious protests against new coal plants that were planned, and those needed post-combustion capture. And so the first UK CCS competition in 2007 specified post-combustion capture on coal. However, I'm pretty certain that if DF1 had actually used post-combustion capture instead of pre-combustion capture, then the project would have gone ahead. I was actually asked by Treasury, why wasn't DF1 using post-combustion capture? And I didn't have a very satisfactory answer. So there you go. Natural gas to power conversion principles were established as early as 2005. This is an IEA greenhouse gas report from 2005. This is electricity costs from post-combustion and from a range of pre-combustion options. So as I say, it's generally reported as cheaper. We'll see a few numbers where it's cheaper, only excepting if you've got low load factors on the gas turbines. Obviously, there's no use temporarily diverting hydrogen from substituting for fossil fuels elsewhere and putting it into power. That gives you no net CO2 reduction. So I think something that does need to be checked is that if you're subsidizing hydrogen, that you don't give a perverse incentive to make power from natural gas when actually via hydrogen, when actually it isn't cheaper, the cheapest way of doing it. Some more modern numbers. This is the same study that Wood did for Bayes, looking at post-combustion capture, natural gas to power, pre-combustion capture via hydrogen, significantly more expensive both on capital and on fuel because it's a lower efficiency. Similar trend actually for pre-combustion on coal. This is integrated gasifier combined cycle, more expensive, and indeed on biomass. Assuming you can do gasification on biomass, go to power, it'll be more expensive than doing post-combustion on a biomass boiler. Bit about gasification. Gasification at the moment is under quite a cloud because of a project in the US called Kemper, which failed, and it failed very, very badly. It was initially estimated to cost $2.2 billion, and it was abandoned, and just the gas turbines run on natural gas after it had cost $6.6 billion. So really serious problem. It should have been stopped earlier. So there's definitely some bad experience with gasification. And if you want to see a recent overview of gasification, there's a reference here to the Power magazine. Biomass gasification has proved challenging. This is another project called Arbor, which was piloted, got to pilot scale, and then failed, fortunately with much lower cost than Kemper. And the problem with biomass gasification is you can gasify biomass with air at relatively low temperatures. You can't go to high temperatures because the ash in the biomass will melt. And you can't get really high temperatures with biomass because it's got a low calorific value. You then have to try and crack the tars that are produced when you gasify biomass at low temperatures, and that can give you problems. There are some biomass gasifiers around, but they tend to be producing a dirty gas containing tar, which is then put straight into a boiler and burnt, which gets rid of the tar very, very quickly. And they're called gasifiers, but they're really staged combustors. So need some more work to prove the technology. For a critical review of UK experience, here's a reference, which I think is gives a reasonable number of examples. And then there's a Supergen Bioenergy Hub report on bioenergy and waste gasification in the UK, barriers and research needs. So there's a few things to look at. However, one thing you can do, and this has been proven, in fact, at the IGCC plant in Netherlands, now closed at Buggenham, is you can put some biomass in with coal and use the energy in the coal to help the biomass react. In fact, the biomass is a little bit like a substitute for the steam that you might put in anyway. And US DOE has put serious amounts of money into two projects. One, a new gasifier study by EPRI, and the other a conversion of an existing gasifier which ran for fairly successfully for a significant period, the Wabash gasifier, that'll be converted from power production to hydrogen production, and they'll put enough biomass in it to be carbon neutral. So we'll get some experience out of the US on these, which will be quite interesting. Whether anybody's likely to do that in the UK, I don't know, but the laws of thermodynamics say it's a really good idea. If you want to gasify biomass, to gasify it with something that's got more calorific value. So if not coal, petroleum coke, possibly waste plastics. Okay, so that's some quick run through hydrogen. So a little bit about oxyfuel. As I said, oxyfuel, you do an air separation to get oxygen, and then burn the fuel with oxygen and essentially get pure CO2. You've done a bit of water removal and clean up. So one option is to burn oxygen mixed in with recycled flue gas into synthetic air at atmospheric pressure in relatively conventional plants. So this is something from the White Rose project, a study that it was DEC funded then, but basically Bayes funded in the second CCS competition from the detailed feed study on an oxyfuel plant on Drax site in Yorkshire. And here you've got a conventional boiler. The flue gas comes out, it gets cleaned up, and then flue gas is recycled, mixed with oxygen. So you get something that burns very like air in the boiler. And it's a relatively conventional plant. There's also a recycle of CO2 to transport coal, pulverized coal from the coal mill. And this sort of approach could be used in boilers, for biomass boilers. It could also be used in industrial furnaces. And one of the advantages, people do actually use some amount of oxygen enrichment in some furnaces just to get higher temperatures. So you can get efficiency improvements that way too. You just have to worry about a little bit about mixing in oxygen and handling oxygen and make sure you do it carefully. But particularly for steel industries, they're handling oxygen all the time. So they have expertise to do that. Another example, which I'm sure a number of you have heard of, is the m-Fetvedt cycle, so just known as the alum cycle. And this uses oxygen, again, and natural gas in this example that can use other gases, and it puts them together in a high pressure combustor. And this is high pressure, it's 300 atmospheres. They're mixed with a lot of CO2. So a few percent of extra products added, and then you take hot CO2 at pressure, you expand it through a turbine, generate the power, and then it's still hot actually, so you cool it down and usefully recover the heat in a heat exchanger made by a UK company, Heatrick, encouraged by Beck. We're actually doing some work looking at how you improve these heat exchangers at Turk on a Bayes funded project. You then cool down this CO2, take out the water that's formed from the combustion of the natural gas, and then compress it and pump it back up to pressure again, heat it up with the recovered heat in the heat exchanger and send it back around as the working fluid. And so well over 90% of the CO2 is just going around in a cycle, the working fluid, and then enough to balance the natural gas and oxygen you putting in. Comes out at high pressure, about 30 atmospheres. It's only got to be compressed by a factor of maybe 5 to go into a pipeline. That saves quite a lot of energy. So this cycle is stated to get pretty high efficiency, nearly as high or as high as conventional cycles, but it captures the CO2 automatically. I'm not going to go through this. This is just people who want to look at it. This shows the cycle on a pressure enthalpy diagram. If you're a lecturer in thermodynamics, which I am sometimes, then it's pretty good because this cycle is a new cycle to talk about, and it combines conventional gas turbines and steam turbines. So it allows you to set a whole new class of exam question. Again, Bayes is funding this work. They've funded some of the previous development, and at the moment there's a feed study going on, or a detailed feasibility study anyway, going on for Teesside on a 300 megawatt plant, and this is based on tests done at 500 megawatts thermal scale at LaPorte in Texas by Net Power. And as I say, now they're looking at what a 300 megawatt plant would look like based on Teesside. So some conclusions. There's definitely multiple options for hydrogen production being considered in the UK. Retrofits and new, possibly steam methane reformers, probably with post-combustion capture. and some new oxygen, possibly air, autothermal reformers, partial oxidation routes using pre-combustion capture. As I said, hydrogen with high levels of CO2 capture is a pretty new development, and the UK cost and performance will be determined by FEED studies and the subsequent full-scale projects. It's hard to prejudge what the options will be. Hydrogen is also definitely being considered for power production, but it has been extensively examined in the past, and this route appears to be competitive only for low load factor power applications, so peaking plant, and when coupled with hydrogen storage. Biomass gasification is also being considered for hydrogen production with CO2 capture, but biomass gasification has proved challenging in the past, especially for synthesis gas production. But co-gasification of biomass with coal is being developed in the US. This allows a particular type of gasifier that generates very high temperatures, rather like a POX, to be used, and those can be quite successful. If you want to use oxyfuel, then atmospheric pressure combustion methods are available using synthetic air, basically proven, and costs appear to be comparable to post-combustion capture. The technology is less proven, but it may be advantageous if you don't have room to do the post-combustion capture. And then finally, we've got the Allen cycle being developed for power applications. There's a feasibility study being undertaken for a project at Teesside. But a significant stage in getting this technology to market will be a demonstration of extended running of a large-scale plant. I don't think we've seen that yet. So we want to see one of these plants really running, for a year or longer at these high temperatures and pressures. So that's it. Thank you. Any questions?